Great. Make full screen. Yes. Okay. Hi, everyone. I'm Andrew. I'm a grad student at the University of Maryland Cybersecurity Center. I'm also a member of the brand new Initiative for Cryptocurrencies and Contracts at Cornell, and I'm an advisor to Zcoin. And I'm going to tell you today about a pair of tools. One's a simulator framework for Bitcoin network, and the other is an all-in-one measurement station for the Bitcoin network. Okay, so let me start by talking about my Bitcoin simulator framework. So there are a couple of approaches to simulating the Bitcoin network. The easiest one is to make some kind of customized model that just is a simplified abstraction of what you care about. Things like this were made like the Symbit model to show off how selfish mining works. The problem with this approach, although it's quite easy and efficient, is that what you put in is what you get. So if the model that you come up with differs from the actual behavior of the Bitcoin network, then you're not actually learning anything about the real Bitcoin network. So a better approach that kind of resembles, not the following talk, but the previous talk, Itai's system, is to have a local private network where you're actually running the real Bitcoin code. But one problem with this is that you don't then have as full control over the network. So it's possible that if what you care about modeling are race conditions, then it may be hard to repeat those. And second of all, you need to actually have a very powerful computing system because you need to run it basically in real time. So that's why you would need about as many cores as you want to have nodes. So the approach that I'm going to talk about is an alternative that's a cross between simulation and emulation. It involves running the real code, but it's going to run it on an entirely simulated network. So all of the network calls are substituted out for a simulated network where we have total control over it. This effectively decouples the virtual simulation time from the real world time. Okay, so the starting point for this is the Shadow framework. This was made by Rob Jansen, who's now at Naval Research Lab. This was his PhD thesis, and it's this framework that works like that, and he mostly used it to study BitTorrent and Tor. And so for my summer internship with Rob, I upgraded the Shadow framework so that it could support Bitcoin. The challenge in supporting Bitcoin is that Shadow is really only made to handle applications that have a very simple event loop, like just one single-threaded event loop with non-blocking I/O. And Bitcoin's architecture is actually really complicated. It has multi-threads. It has a combination of blocking and non-blocking I/O. So we had to sort of re-architecture Shadow to support it. But we achieved that. It works. We have this code, Shadow Bitcoin, online. And what we're able to do is to run simulated networks with up to 6,000 nodes using only 64 cores. So as a result, this runs like 1/14 slower than real time, but that's OK because all of the times are simulated anyway, so the fidelity of the network is fine. But we run into a problem, which is that we need to have some way of bootstrapping what's the structure of the network topology, and so that's actually a question. We don't know what that looks like. So that brings me to the next project, which is Coinscope. The goal of this is to measure the Bitcoin's overlay network topology. So this is something that we actually run scans of the network roughly every 4 hours periodically. I'll tell you in detail like what it is that we do. Our focus is network health, not de-anonymization. We try not to be like chain analysis, so we just we have our UMD Coinscope is like the flag we fly under. We never use more than one outgoing connection to nodes. So we think of ourselves as an extended version of GetAdder. Okay, so relative to the state of the art, everyone knows GetAdder is the gold standard for Bitcoin measurement so far. This tells you lots of details about nodes. You can see which reachable nodes are there on the network. You can see where they're distributed around the globe, what versions they have, but what you don't learn about is how they're connected to each other. Okay, now we think that Bitcoin strives to have a random graph. It does this because every node makes 8 outgoing connections, and those are selected randomly, and it can receive up to 117 incoming connections in addition to that. And the nodes store and propagate to each other information about peers that they might be able to connect to. So in a nutshell, the thing that we do in Coinscope is periodically scrape the entire Adderman contents of every reachable node that we can connect to. Okay, now to understand what kind of data we can get from this, you have to understand how the Adderman data structure is populated, how Bitcoin nodes propagate information about potential peers. So there's 2 ways that nodes share data about the peers that they have. One is that they will relay addresses to each other. This begins whenever a connection is formed, then the initiator of the connection sends its address, and then that node sends that address to a couple more peers, and so on. It sort of percolates through the network. Every node also announces itself every 24 hours for each connection that it has. right? And the other way is that if a node sends a get-attr message, which it does every time that it forms a connection, then the peer receiving the get-attr message sends 2,500 of its addresses along that connection. Okay, now, and the relay part, you actually get the same timestamp. So when a connection is initiated, you get an address message that has the timestamp of that connection time, and as it percolates through the network, it has the same connection time. However, when you get a response from a get-attr, you actually add 2-hour penalty to the timestamp before you store it in your attr_man data structure. All right, and that has this bizarre effect, which is that if you look at a node, like one IP address, and you look at all of the timestamps with the attr messages that show up in all of the attr_mans of all of the other nodes that might know about it, you see these weird clustering effects. You see like one cluster where there are a lot of timestamps corresponding to the moment when the connection was established, but you also see these sort of echoes with varying layers of 2-hour penalties applied, so you can sort of see like a signal that's there representing that initial connection event. And you can actually see that the outgoing connection continues to be updated, so you have this like leading edge that represents a current connection. Okay, so if you collect all of this data, you can stack it all up. This is like all of the attr messages about all of the nodes from all of the nodes, and like the size of the node corresponds to the like number of attr messages the number of address records that have the same timestamp. Okay, and so you can see two like phenomena from this. One is that you can identify when was the most recent connection formed by a node, and the other is that you can see from this kind of frontier of timestamps within 20 minutes new, those are actually active current connections. Okay, so once we do this, we can create these really cool looking snapshots of the network where we can draw every node as like a vertex here, and then all of the edges represent actual established connections between these nodes, and the size of the node represents its degree. So this is really only a subset of the graph. It's not that we get the whole graph this way, because we're only looking at reachable nodes and the connections between reachable nodes to other reachable nodes. We don't learn anything about the mobile clients behind firewalls from this. Okay, and mostly we see roughly what we would expect, that it's nearly random. Nodes have fairly low degree, but we're able to find a bunch of cool supernodes. So this is a snapshot from almost a year ago, actually. And what we found was surprising is that a large number of the highest degree nodes were from the Bitcoin affiliate mining network, which has kind of geo-distributed. Basically, we found 40 different nodes that all have host names with Bitcoin affiliate mining in it and are listed on their website, and they each have 1,000+ connections. So we can identify supernodes with this. Okay, so here's the caveat though. There's a patch in version 10.1 that breaks this. I think that core developers knew that I've been doing this for a while, and it hasn't been something that has like a clear de-anonymization problem against users, but a researcher, Jonas Nick, pointed out that this property that allows us to do this and suggests that it could be used for de-anonymization, so it would be better to patch it. So this technique no longer works, and I can't make nice snapshot figures like that, but arguably it's an improvement to privacy. That wouldn't stop an attacker anyway. There's an alternate technique called TXProbe, which uses a completely different mechanism. It actually uses the mempool and transaction data structure, and it's kind of more invasive, so we don't have any intention of doing that on the live network. It also requires you to spend Bitcoins to pull it off. And another point is that the visible network might not matter so much anyway. Whatever we can see is only what we see by looking at people running the ordinary nodes that follow this behavior. Any sort of private peering agreements we wouldn't see any information about, and those might turn out to be really crucial to understanding what happens in the network with block propagation and so on. Okay, so the conclusion that I want to make is that I would like to see something like measurement being like a deliberate goal of Bitcoin design. Right? So attackers are going to use more invasive techniques than researchers are going to dare to. There are some other precedents for this, like Tor has a nice usage statistics collection that is privacy preserving, but it allows them to collect information about the geolocation of nodes and users. There's also a cool project, Satoshi, which collects like a whole lot of information and records it about the status of your node and its data structures. So it'd be interesting to try to make privacy preserving versions of this that still allow us to get insight into how the network topology is going. Okay, and the only other comment that I want to make is that along this, anytime you do this research into how the Bitcoin network behavior operates, you see that there's tons of vulnerabilities and opportunities for denial of service attacks. So I think that everyone agrees with this now, that it would be a good idea to fortify the peer-to-peer network. And the only point I want to make is that if we make a large change to the network to fortify it, then that'll have other impacts on what we think about block size and other scaling questions. Okay, so we should try to make those scaling questions relative to whatever is the improved network we're able to come up with. Okay, and then with just a final slide, I want to briefly plug this project. We're launching an academic journal for Bitcoin and cryptocurrency research called Ledger. Our main goal is to provide a really useful peer review service that's efficient and effective and is useful to society. And we want to build a healthy bridge between academia and Bitcoin development communities. This is going to be open access with no totally stupid paywall policies. Those are gross. And we're going to do something a little unusual where we're going to publish the reviews alongside articles. I think every academic conference should do this, but we're going to do this in this journal, and we're going to do a bunch of other features that are totally understandable to you, but for some reason other places don't do this, like we're going to timestamp and digitally sign the documents that we publish. And you'll hear more about this from Peter R. That's all. Thanks.
Thank you, Andrew. All right. Awesome.